Let's now look at the differences between addition and condensation polymerization. Now, we saw that in addition polymerization, you have the formation of only one product. But in condensation polymerization, you're going to have the elimination of small molecules such as water molecules. So you'll have the monomers joining together, and as they join together here, you will not have double bonds, but you will have the elimination of small molecules. So if you look at H2O, one of the monomers will lose OH, the other monomer will lose H. So this will form H2O, and this is eliminated. In addition polymerization, you have only one monomer that combines with itself continuously. So you have the same monomer A that combines. But in condensation polymerization, you can have two different monomers that are linked, and that involves the removal of small molecules. And the chain that is produced will contain alternating monomers like this. There's two types of condensation polymers. There's polyamides and polyesters. Let us see the polyamides. Polyamides is commonly known as nylon. Now, in polyamides, you see here, amide, it's referring to the amide linkage. And the amide linkage is this link. This is the amide linkage. So in a polyamide, in a polymer, you will have several amide linkages. So this will be recurrent every time. And the monomers, you have two different monomers. One of the monomer is providing the carboxylic acid. One of the monomer is providing the NH2. So this is the end of the monomers. Now, what is this box representing? The box is representing a long chain in between the carboxylic acid. So this monomer actually looks like this. So you have COOH, and then 8CH2 here, and then COOH again. So you have one carboxylic acid and one carboxylic acid, two carboxylic acids in that one monomer. So that's why it's called a dicarboxylic acid. And this long chain here, this is CH2 8 times. This is what is represented by this box. So every time in the polymer, when we're going to draw the polymer, every time instead of drawing CH2 8 times or writing it like this, we're just going to show a box, because this is part of the molecule that stays the same throughout. The diamine, on the other hand, this consists of, this box here is representing CH2 6 times. So again, it's a long chain, but we don't want to draw the CH2 again and again and again. So we use a box here. Now, this box that you see here and this box is different. This is CH2 8 times. This is CH2 6 times. So here we are going to draw a shaded box like this. This is called an amine linkage. This is called an amine group. So this is another homologous series. We did not cover this homologous series. We did the carboxylic acid homologous series. There's another homologous series called the amine homologous series. And this monomer has two amines, so it's called a diamine. Now here you can see that you can have OH and H that can leave. So you can have the formation of water, because remember that we said that condensation polymerization is formation of the polymer with removal of smaller molecules like water. So this water is going to go out. So let's see the polymerization process. So here I have ordered my monomers in the form A, B, A, B. So it's alternating monomers. And I'm going to have H2O leaving here, here H2O leaving, and here as well. This will also leave with the next dicarboxylic acid, which I cannot show. And here, this OH would leave with the adjacent diamine, which I cannot show again because I don't have enough space. So I have shown 2 dicarboxylic acids and 2 diamines. Now I'm going to start drawing my polymer. So I'm starting in the same way that it started here. So I'm replicating this. Now here, this is gone. OH and H is gone. So the carbon now is linked directly to the nitrogen. So I'm going to have the nitrogen next with the hydrogen on top and the shaded box. Next, I have the nitrogen here. I'm here. And next to the nitrogen, so H2 is gone. So I have carbon, which is connected with the double bond O. And again, I have the same thing. Carbon connected to nitrogen, shaded box, and then nitrogen like this. This continues, and this will also continue. So this is my polymer, and this is nylon. Now, if you want, you can draw the H below. Why the H is usually shown below? Because these two would interact and they would cause hindrance to each other. So just to avoid that hindrance, we usually show this as being down like this instead of being next to each other. So it doesn't make any difference. You can even show it on top. It doesn't make any difference, but you will usually see in textbooks or in exam papers, you see it like this. And you can see here, I have my alternating groups. My alternating groups here. This is my carboxylic acid. This is from my dicarboxylic acid. And this is from my diamine. And what you have over here, this is very important. I have this linkage here. This is called the amide linkage. So C double bond O and H. This is called amide linkage. This is why nylon is called a polyamide. So in a polyamide, you will have multiple amide linkages and alternating boxes. So one empty box and one shaded box. Just be careful that to each box you have similar groups here. So you have C attached, and then to the shaded box you have N attached. Now similarly, if you look at PET is a polyester. So polyester, you will have multiple ester linkages. So the ester linkage, this you are familiar with it. This is the ester linkage. You already know that when we did esters with it. So the monomers here, you have dicarboxylic acid and you have a diol. Diol is from the alcohol family. So when you have one OH, it's called an alcohol. And when you have two OH, so one OH, two OH, it's called a diol. So these two molecules will combine and you have the elimination of H2O. So H2O is liberated. So you can show the polyester. So I'm going to show it directly without showing the process. So it's just the boxes linked by the ester linkage. So you can go on like this. So here I have the dicarboxylic acid, and here I have the diol. Here dicarboxylic acid, and here you have the diol. So again, I have the format ABAB. So this is a condensation polymer, and you will have the elimination of water molecule. So plus, in this case, I have 4 molecules combining, so I have 4H2O eliminated. Now do not forget that you have water that is eliminated. So I have 1, 2, 3, and then this 4. So I have 4H2O eliminated. So this is why it's called condensation. You have small molecules produced. Now, if you are having some difficulty to understand this, you can split it and draw it step by step, where you have the dicarboxylic acid, and then you draw the diol as well, and then you will form the bonds with the alternating monomers. And when you're drawing it like this, you can see how there's 4 water molecules being produced. So 1, 2, 3, and then 4. And then you can see this part here, and this part here, and so on. So you can see how they are connected to each other. Now, what is special about PET is that it can be easy to convert back into the monomers and then repolymerized. So this polymer here can be broken down into its monomers again, and then the monomers can be repolymerized. This can be achieved by using microbes. So certain microbes can break down PET into its original monomers, or you can use solvents, a catalyst, and mild heating. This will save resources and energy and reduce the carbon footprint of the production process. Next, we have a natural polymer, which is protein. Protein is made from monomers called amino acids. Now, amino acids, in the name, there's 2 words here. There's amino and there's acid. So, an amino acid has 2 linkages. An amino acid has 2 parts. So the amino part looks like this. So where you have NHH, this is the amino part. And the acidic part is where you have the COOH. So this is what makes up an amino acid. And here you have H, and because carbon needs to form 4 bonds, you have another group here, R. R can be different groups of atoms. So this R here could be different types of substituents, but the COOH and the NH2 and the H will stay there. These are the constant parts of the molecule. This is the part that changes. This is why it's called R. So similarly, you have up to 20 amino acids. So there's going to be 20 different substituents for R. Now, proteins are called polyamides as they contain many amide linkages. So the amide linkage, if you still remember when we did nylon, the amide linkage is CONH. Like I said, if you want to put the H up on top of the nitrogen, you can. So this is the amide linkage. So proteins are polyamides, natural polyamides. So I'm going to have multiple amide linkages. So I'm going to have a box, amide linkage, a box, and then amide linkage, a box, and then amide linkage, and so on. But because we have different amino acids that are combining, so then I'm going to do different shading. So I can shade one like this, I can shade one like this, I can leave one blank, and I can shade one like this. So you can have different shadings, showing that you have different amino acids, which mean that this part here is going to be different. So the R is different every time, but the C double bond O here and the NH, so this belongs to the same molecule. So C double bond O and then NH, it belongs to the same molecule. So every time in each monomer, you have both the C double bond O and the NH. So in this case, it's not in the form ABAB, it's in the form A, B, C, D, E, F, etc., depending on the order of the amino acids. And each of the amino acid is separated by an imide linkage, and this is the imide linkage here, CONH. Now be careful, there is a difference between proteins and nylon. If you look at nylon here, for the same kind of box, same monomer, you have the 2 carbons. And for this monomer, you have the 2 nitrogen. But for proteins, for the same box, you have carbon and nitrogen as well. So this is the only difference between between proteins and nylon. Now work out the questions in the homework section. This will be corrected when we meet next time, and I will also address issues that you're having as you're doing this part.